Hi, so in this video we're going to get a understanding of the dependent pair type, and to do that we're just going to start reading from the Wikipedia page, and then we'll kind of go from there. So let's get into it. Alright, so here I am just in Wikipedia. I just looked up dependent type, so no big deal. Um, and there's kind of the intro, history, etc. So here's the pi, or dependent product type. So we'll talk about this in a little later video. So in this one, we're just going to start with this dependent pair type, or the sigma type. So we're just going to kind of read through this, and then in the next couple of videos we'll just uh, go into it in a little more detail. So this saying, the dual of the dependent product type is the dependent pair type. So the dependent product type is this thing, so this is its dual. And these are just a couple other names for it. Honestly, they're a little confusing, but and so what it's saying is sigma types can be understood as existential quantifiers. Again, we'll get into that later. It's a little more complicated. Um, and continuing the example above, if in the universe of types, script U, there's some type A, which is of type U, and a family of types B that goes from A into U, then there's a dependent pair type from A to B. And like I said, so we'll do some examples of this, and this will actually make a lot of sense. And this is just saying alternative notations are similar to these. So up here, it's just saying these also apply. Okay. And then so just this next section. So this is probably the stuff we'll actually do first. But the dependent pair type captures the idea of an ordered pair where the type of the second term is dependent on the value of the first. If we have a pair of A and B, which are of type, sigma, x of a, x is type A, to B of x, then A needs to be of type A. So this A right here needs to be this same type. And the value we use for A is going to be bound to this X. And then B is going to be of type capital B. So this B right here is going to be the type of this function capital B applied to X. So this X. So whatever we plug into A here, we're going to apply this big B to that value, and then whatever that type is, B is going to be of that type. Okay, so we'll do examples, but that's what it's saying. And then all this says is if B is a constant function, so this thing, if this is a constant function, meaning it's not dependent on the value of X, then the dependent pair type becomes, which is judgmentally equal to, the product type, which is just an ordinary Cartesian product. And maybe that's what you'd expect, right? So if this B, this function, which is the type, is independent of the x we supply, that's just the same thing as the Cartesian product, right? Because whatever we plug in for A, well, we're going to, this other element, this B, it's going to be of type B, so it's independent of A. So that's all that's saying, and we can do more detail on that. And then this right here, this next section, is just another example. So we'll go through this when we do our examples. So it says, for a more concrete example, taking A, so this A, to be the type of unsigned integers from 0 to 255, and B of A to again be equal to XA for 256 or more arbitrary XAs. So this is, it sounds a little complicated, but we'll do a simpler example. Then the sum type from A to B devolves into this sum here, x naught plus x1 plus x2, and so on all the way up to here. So if we actually do the NLab definition of the dependent pair type, so let's see if we can get that. NLab dependent pair type. So right here, this right here, in the special case that CD is independent of A, this reduces to the product type. Well, that's what we just looked at right here. So this is just saying, if B is constant, then it reduces to the product. So that's what they're saying here. If this C, capital C, that's the same thing as B in the Wikipedia page. then this just reduces to D cross C, so just a normal product type. And this is saying in the special case that D is bool, so this input argument, so in this case, capital A, so it's saying if A is a bool, right? Then this reduces to the binary coproduct, right? So what's a coproduct? That just means the type D plus C. Well, if we look at this example, this is just a 256 coproduct, right? So this example that Wikipedia is giving us right here is the same as this example that NLab is giving us. It's just in this case, it's a little bit smaller because our input set is only of size 2, which is the bools, and this one is size 256. So again, we'll go into that example in a little more detail. But yeah, with that, I think we're good to go. And in the next few, we'll just kind of go into those examples. So, yep, thanks a lot.